Muy buenos días tengan todos ustedes. El seminario Rosalind Franklin se engalana hoy bajo los auspicios de la 15ª Feria de la Ciencia, Arte y Tecnología, y les da la más cordial bienvenida. El día de hoy tenemos invitados muy especiales y hoy por primera vez vamos a tener una conferencia bastante interesante. Hoy les quiero presentar al profesor Jean-François Feller. Él es catedrático de la Universidad del South Britannia o Británica del Sur. Voy a leer un pequeño resumen de su currículum y posiblemente sea un resumen así muy pequeño, ¿no? Él tiene un diploma como ingeniería en química, un grado de maestría en investigación en composición macromolecular y materiales. Tiene un doctorado en el laboratorio de materiales plásticos y biopoliméricos y tiene un par de postdoctorados, en el mismo tema, en plásticos y biopolímeros, y otro de ellos en el Instituto Nacional de Física Nuclear y Física de Partículas. Él es profesor asistente, de 1996, o sea, ya hace un buen rato era profesor asistente de la Universidad del Sur de Britania, en Lorient, France. Es profesor en 2003 como profesor asociado y líder de tesis de investigación. Él es un profesor especializado en física química de compuestos polímeros, de nanocompuestos polímeros, y tiene investigaciones concernientes al desarrollo de los nanocompuestos poliméricos conductivos. Ha realizado diversos trabajos de investigación en fisicoquímica de materiales poliméricos, en composición polimérica de conductividad polimérica, y tiene una serie de artículos en diferentes revistas. Tiene 66 artículos, 5 capítulos en libros, tiene 4 patentes, tiene 15 conferencias y 150 comunicaciones. Entonces, ha dado clases sobre materiales poliméricos en licenciaturas y maestrías, y ha ocupado también puestos administrativos en algunos grupos científicos. Entonces, pues tenemos a un científico con una gran experiencia, y la plática que nos va a proporcionar, nos va a hacer el favor de dictarnos hoy, o la conferencia, es Síntesis y caracterización de materiales poliméricos inteligentes. Démosle, por favor, la bienvenida al doctor Jean-François Feller.
Thank you, Mr. Chairman, for this nice presentation of my curriculum. I would like to thank the organizers also for inviting me to present my research work and teaching activities in the field of polymer nanocomposites. I would like to thank also Ruben, especially for his kind welcome in Mexico. And my presentation will be in 2 parts. One part is the presentation of a master degree, which we are providing in France, in the University of South Brittany, on the topic of nanotechnology. And the second part of my presentation will concern my research activities in the field of smart plastics. Okay, so So what you can see in the background is a nano flower. It's a nano object resulting from crystallization of materials. And now the objective of research in this area is to be able to control this very, very small scale of organization of the matter. So I will present you different examples of this new science. So first of all, I would like to show you where I come from. So Brittany is the west point of France, and France is the west point of Europe. We are close to the sea. So Lorient city is quite a city open to open on the sea. Our university is quite new in France. It's only 20 years old, so it's one of the last university created in France in 1995. There are about 15 labs, 9,000 students. So it's for France, it's a quite small university, and we have about 500 teachers, researchers. So this is the area of Lorient. Lorient is a harbor. Lorient means windows to Orient. It has been a harbor with ships going to India, for example, but also to America in the past centuries. There's also a lot of leisures. Our students like to practice such kind of sports and surf too. It's also a city open on cultural events. We have a first league football team and also an international Celtic festival. So Celtic culture is a specific culture of our region, which is the same kind of culture also as Celts from England. And some Celts are coming from Spain too. So these are the buildings where we are teaching, some labs of chemistry, and our research center. The organization of the courses in France and also in Europe, starting from the undergrad exam, consists in 3 years of bachelor degrees. Then after this bachelor, you can integrate a master degree during 2 years. And after these 2 years, it's possible to make a doctorate in 3 years. The master degree I will present you is called C-Nano. It concerns the nanotechnologies and nanosciences, and particularly the specialty we are invested in at the University of South Brittany is nanocomposites. So I will present you later what are nanocomposites. And it's a degree which is co-habilitated by 4 universities. Our university, the South Brittany University, the University of Occidental Brittany in Brest, the University of Rennes, and the University of Nantes. So these 2 cities are quite large in Brittany. These courses are based on our research activities in the polymers and composite team. So this team is led by Professor Groens, who is a specialist of interfaces and very thin surfaces of polymers. So actually interfaces are very important in composites because it's this very thin layer which will control the properties of the composites. So it's important to control and to understand the behavior of the molecules at the interface between the polymer matrix and the filler, the reinforcement filler. I am leading a small group called Smart Plastic Groups, and our specialty is to develop new materials which are sensitive to their environment So these materials are called stimulable materials also. It's possible to design sensors that will respond to changes of temperature, to changes of strain, mechanical solicitation, and also changes of concentration of toxic molecules. And the third group of the team is led by Professor Ballet, who is developing new composites made of biomaterials, biofibers like flax fibers, hemp fibers, bamboo fibers, dispersed in biopolymers. So biopolymers can be polylactic acid, polyhydroxyalkanoate, etc. So these are sensors made of nanocomposites. I will present you this later on. So why studying nanotechnologies? You can see on this graph that the evolution of the research field is quite slow for some old fields like physics, chemistry. It's decreasing for some kind of this kind of fields, miniaturization, solid state energy, meaning that these fields are not expected to develop anymore after, let's say, 30 years, whereas these new fields are emerging fields and they are expected to develop a lot in the field of nanomaterials, nanocomposites, biomedical applications, microelectronics, etc. So the nanotechnology field is at the interface between several fields. So if you study this, you need to have also some skills in classical fields like life science, technology, tech media, electronics, energetics, and chemistry. So this is the content of the courses of the master degree. So there are some theoretical courses like nanophysics, nanoelectronics, which is really a new field because it's you may know that the physical properties of materials can change when you are decreasing the size of observation. So the physical properties of materials will not be the same for carbon, for example, if you are studying nanoparticles of carbons or large parts of carbons. So it's important to know the changes of properties due to the decrease of the size of the material. So all these courses will deal with the new fields related to the decrease of size of observation. You need new tools of characterization to be able to observe these small things, small particles. So you need new kinds of microscopes like atomic force microscopy, transmission electronic microscopy, high field emission scanning electronic microscopy, some also spectroscopic tools to be able to observe the fabrication and of these new nanomaterials. And then there's a part of the courses which are practical, so through projects or lab experiments. And the specialty we are teaching in Lorient is based on our research activities. I will develop them later on, surfaces and interfaces. So to understand the molecular interactions between nano objects and polymer macromolecules, the understanding of the conductivity, electrical conductivity of nanocomposites, the ability to functionalize nanofillers, to bring new functionalities by chemistry, the development of hybrid polymers, taking the advantage of some new chemicals and some new nanofillers, and the blend of all these different compounds through nanophases. So this is for the first semester from, let's say, from September to January. And then the second semester of the second year of master is a training, an internship, either in a company or in a research lab. So if you don't know this field, you can have a look to the website of this university. So Lorient is specialized in multifunctional polymer nanocomposites. The University of Nantes is specialized in the synthesis of nanowires, nanotubes, optical properties, and advanced spectroscopy. The University of Rennes is specialized in nanomagnetism, nanophotonics, microfluidics. So particularly they have clean rooms to fabricate electronic compounds at the microscales and some of them at the nanoscales. And the University of Brest is specialized in magnetic nanostructures. So you have here pictures of nanocircuits, microcircuits, nanotubes, nanowires, which are used to design new technological applications. Thank you. Oh, okay. So, some professors are specialized also on the modeling of the interactions, of chemical interactions between new molecules that can be organic compounds in the atmosphere, or you can think about medical applications. The interactions can be modeled with the substrates of the nanocomposites. These are tools of characterization, very performant microscope, electronic microscopes, and this is an image obtained by atomic force microscopy. And here you can see some students in the clean room. They are dressed like that to prevent any dust, any particles to contaminate the micro devices that they are fabricating. So this special part of the lab is conditions with special filters to remove all the particles. And these are nanoparticles observed by microscopy as well. So we can use also the nature to mimic some existing systems which are nano-structured. If you have a look to the fingers of this lizard called gecko, that you may know, this lizard is able to climb any kind of surface, even a glass surface, very smooth surface, just because the end of his fingers contain this spatula, which can adhere on any kind of surface. And so this spatula have a special structure. If you magnify the tip of the fingers, you will see a first level of organization at the micro scale. And if you magnify once more the structure of the spatula, you will see small pods, small spatula, and this time it's at the nanoscale. So there are different levels of organizations at different scales. And the interest of this is that the surface of contact with between the fingers of the lizard and the surface he wants to climb are huge, because there's a division of the matter which is improving the surface between the surface of contact. So this is adhesion based on van der Waals interaction. I don't know if you know that. The adhesion can be chemical adhesion if you create chemical bondings between the different surface, or simple non-covalent bonding. So in this case, it's simple contact forces that will allow the lizard to climb. So this structure coming from nature has been reproduced here artificially by the fabrication of a nanoforest of carbon nanotubes. So based on the the same principle, the multiplication of the surface, it has been possible to lift this weight simply with addition, interactions of van der Waals on this small surface. So it's possible to extrapolate this case to this movie, in which Tom Cruise is climbing also on surfaces with special gloves. So it's possible to imagine that the gloves are containing such nanotubes forests, which can be activated by some electricity, and which will enable him to climb, like the lizard. So this is enabled by a new nanotechnology. So what are nano objects? You can see that the scale is very small. The typical size of the nano object is a couple of tenths of nanometers. Here you can see carbon nanoparticles, which are agglomerated together. So you need a special microscope to visualize the scale of these nanoparticles. So this can be electronic microscopy or atomic force microscopy. And you can have also nanofibers, nanotubes, which have a very high shape ratio. Typically, the nanotube's diameter is 10 nanometer, and they can be as long as several microns, in some cases several millimeters. So you can imagine very long filaments that are completely entangled. And the interest of this nanofiller is that they can make polymers, which are initially insulating most of the time. You can make them electrically conductive with only a small amount. So these nanoparticles can be used as a dopant of insulating materials. So you can disperse these nanotubes or nanoparticles in a wide variety of polymer matrices, and you can also control the structure of the polymer. Here you have a double gyroid morphology with two polymers, and you can imagine to locate the nanoparticles in one or the other polymers. It's what is achieved here in this nanostructuring of two polymers. So here you have a layer in blue of polystyrene, then a second layer of polyethylene propylene in green, and you can see that it has been possible to locate silica nanoparticle in this polymer and gold nanoparticle between the two polymers. And this is making possible the development of new materials for optics, for example, but not only, with a very nice structure. Here the stripes are 50 nanometers. So it's very complicated to be able to control the structure of the material at this scale. So it's possible to use such kind of nanocomposite to make sensors, so sensitive materials, sensors that can detect gas molecules. So you need to put the sensor on an electrode, and then the interactions between the organic molecules and the sensor will trigger an electrical signal that you can analyze. If you combine different sensors like this, you can make an electronic nose which will allow you to separate different vapors that can be present in the atmosphere, vapors of solvent like chloroform, ethanol. In the field of composite, you can analyze styrene, which is released during the synthesis of the composite, for example. You can also develop gas barrier polymers, which can be used to prevent oxygen to go through membranes. You can imagine such film for packaging, for example. If you want to protect tomatoes from outside, you will leave oxygen cross the film, and you will not leave moisture leave the tomato. So you can make specific barriers by the dispersion of nanoplatelets, which can be clay in this case, and the clay will make nanobarriers to prevent the diffusion of gases through a very thin film of polymer. You can use this also to protect cloths against fire, to ineffugate textile, for example. It works very well with cotton. If you want to prevent the burning of cotton, you can put a very small, very thin layer of nanoplatelets like this to protect the textile. So it's possible also to design biodegradable nanocomposite that will have different times of degradation. If you are making objects like this for food, the lifetime of this object is very small. It's a couple of hours. So you don't want them to, you want them to be degraded very quickly after they have been used to eat food. So you will develop polymers with high rates of biodegradation. If you want to make a part of a biodegradable polymer for a car, for example, you want the part to last 10 years or 6 years. So you want a small speed of biodegradation. So it's possible to adjust the speed of biodegradation by the introduction of nanofillers. Nanofillers like graphene, which is a single layer of carbon atoms, can be used also to make intelligent packages, which can monitor the degradation of food. Nanocomposite can be also used to monitor the deformation of materials. Here you have the scheme of a sail for boats. It's a textile, and you can put on this textile a very thin layer of nanocomposite that will be able to follow the deformation, as you can see on this graph. So you can follow the deformation, and not only that, you can also follow the damage of the textile, because if you make cycles, you will see that the cycle will not be necessarily reproducible. This means that the sail is going to be damaged upon the application of the strain. You can also design heating device to produce heat from current, but not only that, you can design your systems so that the temperature will be controlled automatically without any electronic device. Because in the composite there will be nano switch that will disconnect themselves if the temperature is increasing. So at the nanoscale, increasing the temperature will result in the disconnection of the conductive networks upon temperature. On this figure you can see that when you apply current to the two conductors, the nanocomposite is heating, and you have a gradient of temperature between the two wires. And then the temperature can be automatically adjusted. If you want to improve the thermal properties, that is to say the diffusion of the heat, you can also dope the nanocomposite with thermal fillers. So thermal fillers can be carbon or ceramics, like alumina, but also boron nitride and other kind of ceramics, which are much more conductive, thermally conductive than the polymer itself. So this is the end of the first presentation concerning teaching. If you have questions, you can obviously ask them to me, and I will try to answer you.
Hay una segunda presentación. Do you want some question about this?
If some students have some question, I can answer.
Bueno, si alguien tiene alguna pregunta acerca de esta primera parte de la plática, pues con todo gusto el doctor Feller nos hará el favor de contestarla. Bueno, entonces, pues continuamos.
Okay. So I can show you now what we do in our research group. So I told you that we are developing stimulable materials, smart plastics. So this smart plastic can be small but smart. Sensors can be used to diagnose diseases, for example. In the body, you are producing many organic molecules, like acetone, alcohols, and many others. It seems that you are able to produce more than 200 different kinds of organic molecules. So it's possible to collect these molecules from your breath. And the analysis of the amount of molecules in your breath will allow to diagnose if you have a disease or not. So there are many researches now to develop this topic, to diagnose, for example, cancer of breast or other kind of cancers, diabetes, and it's developing a lot. There are still important issues to solve before it will be available commercially, but it's a very active field of research. So we are making nanocomposite sensors to analyze such vapors. I told you we are making also strain sensors to monitor the deformation of composites. Here it's also able to monitor the deformation of a textile, like here it's a stocking made of elastomer. So there are large deformation in such kind of materials, which are possibly monitored by our sensors. And we are making also sensors for smart packaging. So which kind of properties are we looking for to develop such materials? The materials must be, for example, thermostimulable. This means that if you increase the temperature around the material, you will get an electrical signal like this one. Or you can look for chemostimulable material. This would mean that if in the environment of the material there are some molecules which are diffusing in the material, you will also get a signal. And it is the same for photostimulable. Such material can be responsible for light, magnetic field, or simply the application of a pressure. On your mobile phone, some of them are sensitive to pressure. So you can expect that they are made of same kind of materials. So piezoresistive can be used to make pressure-sensitive materials and also strain-sensitive materials. And of course, some of them are electrostimulable. If you apply a current, you will have a mechanical response this time. So we have developed a special process to design these sensors based on spray. So spray is like paint, for example. And the interest of this spray is that you can control the structure at the different scales of the observation. Like for the gecko foot, you have the scale of the droplets, which is about 50 microns. And in these droplets, you have another scale, nanofillers, nanotubes, or nanoplatelets, like graphene. And moreover, you can also control the fabrication by the number of spray layers that you will put on the electrodes to make the sensors. So here I can adjust the layers, which are very thin, about 40 nanometers thin, each layer. And I can build the 3 dimension like this. Such kind of sensors have been fabricated. It's possible to use them to monitor the atmosphere. Due to the pollution, sometimes some toxic molecules like this one can be present in the atmosphere at quite high level. So if you if you are exposed too long time to such molecules, you will develop cancers and such diseases. So you can find pollution outside, and you can find pollution also inside. Due to the different kinds of paints and materials and cleaning products that you are using in the buildings, there's a release of toxic molecules. If you breathe this too much, then you will be also ill. So it's not stupid to design sensors to put inside building to monitor the amount of toxic molecules. So you can use chemical sensors also to monitor the degradation of food. There's about 30% of the food which is spoiled because it's degraded before you can eat it. So it can be interesting to put a sensor inside the packaging to know if the food is spoiled or not. Imagine some fruits which are traveling on long distance. You never know if during the transport the fruits will not degrade. So it can be a way to automatically control the degradation of food during the transport or during the storage in the shops or even in your fridge. It's possible also to monitor the disease development. The principle is quite the same. It's based on the production of organic compound by bacteria or by cancerous cells. So different specific bacteria will produce specific organic molecules like toluene, cetone, even methanol, ethanol. And these molecules are not the same depending on the place in the body they are localized. So you can compare the production of these molecules and be able to make a diagnostic. So it's not completely effective, but it's developing very quickly. So the principle of electronic noses is also mimicked on the mammal sense of olfaction. So you can see here inside the nostrils of the mouse, but inside your nostrils it's the same. You have many receptors which are sending signals through your neurons to the brain. And it's a quite complicated system, of course, in the brain. What we need to know is that these sensors are not specific. This means that you don't have one sensor sensitive to methanol, the other to ethanol, etc. They can be sensitive to many others. So the interest of the non-specificity is that you can identify new others that you don't know. So it's possible to train. The nose can be trained. When a baby is smelling others, he's not able to identify the others. So this is the first point. These sensors are non-specific. The second point is that the area of the brain are multiple. For only one odor, here it's a vapor of butanol, you can see that many areas of the brain are concerned. So it's a massively parallel analysis of the data. So it's, of course, a very sophisticated data analysis system. So we try to mimic this with our sensors. We have many sensors in parallel, and we analyze the signals of this sensor, and we make a processing of the data through such kind of graphs, which are projections in special spaces of the data, in order to identify, to separate the vapors. And also what we want is to quantify how many molecules of these kinds are in the atmosphere. Right now, our sensors can detect as few molecules as ppb, hundreds of ppb, let's say, which is parts per billion. So it's only a couple of molecules in such room. So it's possible to reach a very high sensitivity. Now, what is important also is to reach a good reproducibility. It's not enough to be sensitive. You need to make sensors which will be reproducible. And also, you need to make sensors that will be selective to be able to discriminate between the different vapors. So to do that, we have developed a particular technique, which is the control of the junctions between the nano objects. The electrons are circulating in the network of nanoparticles, and they are jumping from a particle to the other. So if you control the way the electrons are jumping, you can control the properties of the sensors. So we developed different strategies to coat, to graft, chemically graft carbon nanotubes. And particularly, we achieved the coiling of the nanotubes by natural molecules like amylose. Amylose is a polymer that you can find in starch, in flour. So this molecule is known to be able to make coils, to make helices. So you can use these helices to coil the nanotubes. And then if you assemble such objects, you will be able to control the distance between the objects by the coating with a specific molecules. So in this case, the molecule is used to control the distance between the nano objects, and it's also used to detect organic gases. So there's a double use of the molecule. It's used for the selectivity of the sensor and also to control the junctions between the nanotubes. When you are using foils, like graphene foils, the problem is slightly different from tubes, because the geometry, the morphology of the foil is completely different. So if you do nothing, you will pack the foils one onto another, and it will be very difficult to make them sensitive to organic molecules. So it's the reason why we have introduced some spacers, some molecules that will introduce spaces between the foil to allow the disconnection of the foil. If you have no disconnection, you have no electrical signal behind, so your system is not sensitive. So the use of the disconnectors is to introduce space, but also to introduce functionality. So you can graft such kind of molecules, which can be polyionic liquids or conducting polymers. So this polymer is used also to make photovoltaic cells. It's able to conduct electrons in its backbone, because there are double bonds here, so the electrons can circulate in the backbone. And the electron circulation is modified in the presence of organic molecules that you want to detect. So in this system, you can take benefit from the conductivity of the carbon and from the conductivity of the polymer itself. So if you have a look to the morphology of the system, it's like a house of cards, because these foils have been sprayed and they are randomly organized on the surface on which they are sprayed. If you use a very thin layer of this material, it can be even transparent. So you can spray it on a transparent film and make a transparent sensor. So here you have an idea of the different materials. Some of these materials can be sensitive to methanol if you graft on them some hydroxyl functions. Some other materials can be sensitive to toluene if you graft on the material some aromatic ring, for example. So it's possible to adjust the selectivity of the nanocomposites by chemical grafting. Then you want to measure the amount of molecule. So you need signals that will be proportional to the amount of molecules in the environment of the sensor. And then you can try to find the model that will predict the amount of molecules depending on the amplitude of the electrical signal, which is plotted here. Here you have the amplitude of the response of the sensor depending on the amount of molecules. There's a limit, of course. You want to see and to know which is the limit of the amount of molecules that your sensor can detect. So the limit can be evaluated by such ratio, which is the ratio of the response on the noise of the signal. So in our case, it's only a couple of hundreds of ppb. So these were the chemical sensors. Now the health monitoring sensors. So sensors able to monitor the health of composites. So composites can be used to make racing sailing boats, which are built in Lorient City. There was recently a race across the Atlantic Ocean with such boats. They can reach speeds of about 80 kilometers per hour on the sea. So it's really like a race car. It's quite dangerous, so it's only for specialists. And the materials, of course, are submitted to enormous solicitations, to waves, to wind, and so on. So quite often they are broken, even if they are made of the strongest materials known for this kind of application, that is to say carbon fibers with epoxy polymer. Even in this case, they can break. So it can be interesting to anticipate the breakage by the introduction of sensors inside the composite. So you will measure the resistivity of the composite, and if it is going to break, you can trigger a signal of alarm to prevent the complete destruction of the composite. So you can do this on composites, and you can do this also on sails. Last application is production of energy from current through these materials. I present you already cable which are able to warm the ground. You can see here a thermography, infrared thermography of the ground, heated by the cables put inside the ground. So it's possible to adapt the temperature of the ground and to warm rooms. It's possible also to use such material to make intelligent textiles. You have here a fiber made of nanocomposite, which is able to heat, to warm. So you can imagine textile made of these fibers able to warm, to prevent hypothermia, for example. You can see here that these fibers has been weaved. And such fiber can be sensitive also to chemicals. So you can use them to analyze chemicals on cloths. It has been done for firemen to prevent them from being burnt by the fire. So I would like to thank my partners, collaborators, and also our sponsors, Europe, Brittany region, and Interreg program, and the lab with which I am working on these topics. So if you want more details about the activity of my group, you can visit this website. And I thank you for your attention.
Bueno, pasamos a la sesión de preguntas. Las pueden hacer en español, por favor, no hay problema por eso. A ver.
Well, there is your university experiment related with the nanotechnologies, like the example of the particulars and the fingers.
Sorry, I didn't get the first part of your question.
There in your university, some some experiment with the nanotechnology, like the example with the particles in the fingers, like the thumb.
Your question is it possible to do this sample in our university? Yeah, of course. Some of my students are working on this in PhD or in master degrees. And if you want to make microsystems with processors, or it's necessary to go in a clean room. So this is not possible in our university, but in another university, in Rennes, for example, which is about 100 kilometers from Lorient, because it's quite expensive, quite complicated. You saw the special equipments the people need to wear. So it's possible to make experiments of such kind, but it's more complicated and expensive. Whereas if you want to develop nanocomposites, like I do, it's more low cost, and you don't need a controlled atmosphere with no particles, no dust, and so it's more easy to handle experimentally. Thank you.
¿Alguien más? Adelante, por favor.
What can be the benefit or the utility about graphene in a technology?
Which kind of behavior we can expect from graphene?
What are the benefits? She's asking what are the benefits
From?
from the graphene?
Yeah, graphene. So graphene has extremely exceptional properties with mechanical properties. So it can reinforce materials, increase the modulus, elastic modulus. It can also make gas barriers, and it is also extremely conductive, electrically conductive, extremely thermally conductive. This means it's more conductive than copper. And it has a very high specific surface. Some of the foils can be several microns of length on only 1 nanometer of thickness. So it's like the curtain, but the curtain would be 10 times the size of the room with the same thickness. So it's really an exceptional object. Now it's also difficult to take benefit from these properties when you want to assemble lots of these parts. So the complexity results from the assembly of the graphene foils, because you cannot get something with only one foil. It's difficult.
¿Alguien más? Bueno, yo no quisiera irme sin hacer una pregunta, nomás que mi inglés es muy malo y quisiera traducción, ¿no? Doctor Feller, si estamos ante una nueva revolución tecnológica en el área de nuevos materiales, ¿no tenemos el riesgo de caer en una nueva fuente de contaminación con materiales, por ejemplo, más estables, que pudieran durar millones de años y que no sean degradables? ¿No estamos ante una posibilidad de ese tipo?
We're in a new revolution of materials. In this case, he's asking if we cannot have a contamination, like a pollution.
Okay. You mean cytotoxicity or something?
No, with materials with high stability, and the materials can make a life for millions of years, maybe.
Okay, so there are two parts in the question. Maybe classical materials can be toxic. Like I said, if you have an agglomerate of wood, you can have a release of solvent molecules that can be toxic. So you can not decrease their toxicity, but control it by putting some sensors of nanocomposites. It's one thing. or you can use special filters to remove toxic molecules from water, from air, and so on. But also, nanomaterials can be toxic themselves. Nanoparticles, if you breathe nanoparticles, you will be ill. Like if you breathe toxic molecules also. So it's necessary to handle these nanoparticles like chemicals in special boxes and not to breathe them.
Sí. Doctor, my question is about the other kinds of materials. For example, typical materials that we can use in the industry. For example, material with high stability. Then you can quite of the media and for materials that the contamination or pollution is only for the create that kind of materials, not for toxicity. O sea, for example, you remember the diapers that in the past have a life of 500 years, and now we can make materials with.
Okay.
So
you mean, is it possible to make high durability materials?
Yeah.
Dice que hacer materiales con menor durabilidad de degradación.
But the market demands materials with high resistance and with high durability.
I told it's possible to increase mechanical properties, like tenacity. If you put nanotubes in a resin, even in a composite with carbon fibers, you will increase the tenacity. I didn't mention also there are many applications in the energy field, like batteries, supercapacities, photovoltaic cells, which are using graphene and fullerenes and nanotubes. And so they are quite stable. Carbon is quite stable to temperature and to chemical products. So they can be used to make very stable materials.
Bueno, ¿alguien más? Bueno, antes de despedir al doctor, yo quisiera que pues se pusiera la camiseta de la Universidad de Guadalajara. Si,
Before you go, he would like that you wear the t-shirt of the university.
Ah.
no, it's a joke.
He's just kidding. He just wants to give you.
Agradecemos, le vamos a dar reconocimiento al doctor Feller por su presentación, le otorgamos el reconocimiento.